So up till now, we've looked at the integrals with respect to x. So we've looked at the integration in the x direction. What that's allowed us to do is look at curves and calculate the area between the curve and the x-axis. So an area like that. So we've looked at areas here like this. And in order to do that, we know we've had to calculate the integral from a to b of our function f of x dx. So with respect to the x-axis. However, what happens if we want to switch that around? What happens if I want to take a curve and find the area not between it and the x-axis, but here, between it and the y-axis? How do I approach a question like that? Well, that's what we're going to look at in this video here on y-axis integration. Now, the ultimate question is how do we calculate the shaded area that is here if we've got a function y equals f of x? Well, normally our limits are here on the x-axis, but in this case I've given them on the y-axis. When we integrate, because that's where it's going to go, we're going to have to integrate with respect to y. But my issue is that my function is dependent on x. My function has some form of dependence on x. How do we deal with that? Well, we deal with it quite simply. What we have to do is change the subject. So we have to take it y equals f of x and rewrite it in some form. We get x equals f of y. So we take the function here, change the subject of the formula, and make it x equals something, and it's an equation in y. Once we've done that, we can do the integral from a to b of f of y dy, i.e. we can do the integral in the y direction. This time though, instead of with respect to x, we're working with respect to y. So we've changed the variable we're going to work with and that we're going to look at in the direction our curve is pointing in the area that we're going to look at. So let's have a look at what this means, because this could be quite a complex thing, but actually seeing it in action, that would be the easiest way for you to understand it. Imagine I wanted to calculate the shaded area in this section below. So it's the section here where on the y-axis it goes from 1 to 8, and it's the curve y equals x minus 2 cubed. Now in order to do that, because the area is in the y direction, remember I want to do the integral from a to b of f of y dy. Now in order to get that, I've got to take this function here, which is currently a function with respect to x, and rearrange it so I get x equals something with respect to y. So to do that, think back to when we did changing the subject of the formula. Swap x and y, and then rearrange it to get x equals. So I've got y equals x minus 2 cubed. So I swap and I get x minus 2 cubed equals y. And now I've got to do this and find out what I need. So take the cube root of both sides. I get x minus 2 equals the cube root of y. I then get x equals, well, cube root of y, let's write it as y to the power of a third plus 2. So now I've got a function here where x equals that. So what I'm able to say is my f of y equals y to the 1/3 plus 2. That there is now the function we are going to integrate with respect to. That's what we're going to work with. So what I can now do is substitute it in here along with my limits, which I know because they're given there, and calculate my area. So I know the area in this case is going to be the integral from 1 to 8 of this function here, so y to the power of 1/3 plus 2, this time with respect to y, dy. So I've got to calculate all of this and then work it through. So integrate these parts, so y to the 1/3, we add 1 to it, so we add 3 over 3 to that, and we get y to the power of 4/3, and then we divide it by the new power, which is 4/3, plus 2 times x, and it's between 1 and 8. Let's simplify this part here at the beginning. So y to the 4/3 divided by the 4/3, switch that around, I get 3/4. Y to the power of 4/3 is the cube root of y to the power of 4. I've then got plus 2x. And again, it's from 1 to 8. Now this looks a little bit more complicated, this bit, but actually when we plug these values in, it'll end up working out quite nicely. So I have to do it at the upper limit. So in this case, I've got 3 over 4 times the cube root of 8 to the power of 4 plus 2 times 8. Take away at the lower limit 3 over 4 times the cube root of 1 to the power of 4 plus 2 times 1. Calculate this upper limit here. Well, cube root of 8 is 2. 2 to the power of 4. 2 2s are 4, then 8, then 16. So I've got 3/4 times 16 plus 16 in the first bracket. Take away, well, cube root of 1 is 1. So in the second bracket, it's going to be take away 3/4 plus 2. Simplify both brackets here. Well, 3/4 times 16. 1/4 of 16 is 4. 3/4 of it then is 12. So 12 plus 16. 28 in the first bracket. Take away 3/4 plus 2. Well, that's 2 3/4. Stick it all over a common denominator though, and that gives you 11/4. Take the two of them away from each other. What you'll end up getting is 101/4. Stick the 28/4, make it a common denominator to be able to do it, and then you'll get your answer. So 112/4, take away 11/4 gives you that. So it's 101/4 units squared. None of the basic general ideas change. The way we integrate doesn't change. The way the powers go, so up by 1 divided by the new, that doesn't change. The way the limits go in, no, that doesn't change. Upper limit, take away the lower limit, that's still it. All that changes is what we're integrating with respect to, which is this part here, integral with respect to y of f of y. And in order to get that, all we have to do is change the subject of the formula. So we've got y equals this, we change it and make it x equals, just as we've done down here, and that then becomes the f of y we integrate, which still gives us the same sort of idea and the same general steps.